In this section, we're going to learn about systems of linear equations in two variables. Last time, in the last section, we looked at a single linear equation in two variables. We saw that its graph was a line. Its graph in the plane was a line. Now we're going to look at a system of two equations in two variables, and usually we'll refer to these as a shorthand as 2 by 2 systems, meaning two equations, two variables. So a system of linear equations in two variables is a pair of equations, and usually we'd like to consider them when they're written in both in standard form, like a constant times x, a constant times y, and then a constant term by itself on the other side. If we have that pair of equations written in this form, we say that the system is in standard form. So in these equations that we're going to be solving, you know, our two variables are usually x and y. It's also pretty common when you're working with systems of equations to have variables written using the same letter but different subscripts. So, you know, depending on other resources that you might look at, you might see them write it as x1 and x2 instead of x and y. That's super common. We're going to focus on these 2 by 2 systems and how, in a couple of different algebraic techniques we have to solve them. Before we move on to techniques that can help us solve larger systems of equations, and we'll be solving some 3 by 3 systems by the end of this chapter. So when we solve a system of equations, what we mean when we say we're solving a system of equations is that we're trying to find a pair of values, one for x and one for y, that satisfies both of these equations at the same time. Now, let's look at an example. Here we're given a system of equations, 2x plus y equals 8 and x plus 3y equals 9. First, they say let's sketch the graph. You know, we know how to graph each of these, right? We know they'll each be a line. So let's graph both of these. I'm going to number these equations. So I have equation 1 and equation 2. And then I can, because we're going to graph them on the same set of coordinate axes, and then we can just sort of identify each line. So let's work with the first equation first. I'm just going to graph this by getting my intercepts. So our x-intercept, recall that to get the x-intercept we set y equal to 0. And if we set y equal to 0 in that first equation, the equation we get is 2x equals 8. And that means if we divide both sides by 2, that means x equals 4. And so our first line has an x-intercept of 4, 0. And to find the y-intercept in that first equation, we're going to set x equal to 0. And if we set x equal to 0 in that first equation, we get the equation y equals 8. That's our y-intercept, right? So the first equation has a y-intercept of 0, 8. Now before I graph this line, I'm actually going to get the intercepts for the other line first, because I want to make sure that when I draw it, when I sketch it out, I know exactly where both intercepts, or the intercepts for both lines are, so that I can use an appropriate scale. So let's work with the second equation. We're going to find the x-intercept here. To find the x-intercept, we set y equal to 0, and when we do that in the second equation, we get the equation x equals 9. So that has an x-intercept, our second line has an x-intercept of 9, 0. And for the y-intercept, we set x equal to 0, and when we do that, we get the equation 3y equals 9. And dividing both sides by 3 gives the result y equals 3. And so the second line has a y-intercept of 0, 3. So now I'm going to sketch both of these lines. I need my x-intercept, my x-axis to go out as far as 9. I need my y-axis to go out as far as positive 8. So let me just make my marks. So there's 9. And here's 1, 2, 3, 4. That's the x-intercept of the first one. And then for my y-axis, I need to go up as far as 8. That's the y-intercept of the first line. The second line has a y-intercept of 3. Alright, so let's sketch the first line. It has an x-intercept of 4 and a y-intercept of 8. So there's line 1. And for the second line, that has an x-intercept of 9 and a y-intercept of 3. And there's the second line. So now, take a look at this. This first line, right, the one that goes through the y-intercept of 8 and the x-intercept of 4, we know that that is a visual representation of all the points that satisfy that first equation. Any xy pair that satisfies this equation, 2x plus y equals 8, is going to lie on, that line right there. Likewise, any point that satisfies that equation, x plus 3y equals 9, is going to lie somewhere on that line. And if I'm looking for a solution to the system of equations, I'm looking for the point that satisfies both equations at the same time. Well, visually we can see that point has to be right there where those lines cross. So geometrically, we kind of have this this concept now of solving a system of equations means we're trying to find the point where those lines intersect. So the intersection is the solution. And we just want to know what that point is. When we graph them, we could say, it looks like it's somewhere around the point 3, 2. When we graph them, that's sort of the best we could do is say, oh, this is where it looks like it is, so it's not maybe the most satisfying way to actually solve, although it's a good way to kind of get a sense for where we expect the solution to lie. Before we look at some algebraic techniques for solving that will be more precise, right? They'll give us actual precise solutions. I want to spend a couple minutes and just talk about what's possible. So when you have a system of equations, it is possible that that system of equations will have a single unique solution. That is just like what happened here. There's only one point where those lines will cross, right? And that's what we see here in this first box on the left. There's only one point where these two lines will cross. As it turns out, it looks like that's at x equals 4, y equals 1. There's those two lines, because they extend indefinitely in either direction. They're not going to turn around. They're not curved lines. They're not going to be able to cross again. It's also possible that you might have two lines that never intersect, right? Like the lines are parallel and there's no point that they share in common, which means there is no solution to that system of equations. And the third possibility is that maybe those two equations actually define the same line, in which case there are infinitely many solutions, right? Any point on that line is a solution to the system. We're going to look at two algebraic techniques for solving these systems, and we'll be able to solve a system that has a unique solution, and we'll also see how these algebraic techniques can tell us if we're in one of these other, situations where there's either no solution or infinitely many solutions. So the first technique here is called the method of substitution. And the way it works, here we have a procedure outline, and we'll just sort of work it out via, by example. But the idea is you pick one of the equations and solve it for one of the variables. Ideally, you make this choice so that you end up with the least amount of work to do, but it'll work either way. Like no matter which equation you pick, And then no matter which variable you choose to solve for in that equation, it'll work. Sometimes there are choices we can make that'll make our work easier. So you get an expression, like say you get x in terms of y or y in terms of x from that first equation. Then you substitute that expression for that variable into the other equation. It's really important that you pick the other equation when you do that. And then when you do that, you're going to have an equation with a single variable. So solve it. Then you get one of those values. You get either x or y. And once you have that, you can plug that value into either of the two equations and get the value of the other variable. So let's see how this works by example. We're going to solve this equation. I'm going to number these equations again. And, you know, there's two choices I could see here that would be make for easier work. Would be to either solve the first equation for y or solve the second equation for x, just because those coefficients are 1, so there's very little work involved in solving those. So I'm going to go ahead and solve the first equation for y. So that equation is 2x plus y equals 8. If we subtract 2x from both sides, we get y equals 8 minus 2x, or negative 2x plus 8 if you prefer. The next thing we do is I picked equation 1 there, so the next thing I'm going to do is plug this in for y in equation 2. So let's substitute into the second equation. So that equation is x plus 3y equals 9. So this will be x plus 3 times, now y is equal to 8 minus 2x equals 9. Now this is an equation with one variable. Let's solve it. We know how to solve a linear equation of one variable. Let's distribute that 3, so we get x plus 24 minus 6x equals 9. I'm going to subtract 24 from both sides. And then on the left side, we have x minus 6x. That's a negative 5x equals 9 minus 24 is negative 15. And now dividing both sides by negative 5 gives us x equals 3. So we know one value, one of the values that we're looking for. Now we need to find y. Now look, in this process, right, we said, in the very first thing, we said let's solve the first equation for y. So I have an expression for y in terms of x. So I'm just going to use it. I know that x is equal to 3. So now the last thing I'm going to do is solve for y. So y is 8 minus 2x. That's 8 minus 2 times negative 3. 2 times positive 3. 8 minus 6 is 2. Y equals 2. And so the last thing we do, once we have both the values, is now we're going to state what our answer is, because the answer isn't two kind of separated values. I want to state them as a pair, because really we think of it as the coordinates of a single point. So you can state the answer as x equals 3, y equals 2. There's the solution. Or some people like to give it as coordinates of a point, and that's fine. Just make sure that if you give the answer this way, the x coordinate has to go first. Note that here we just solved the system algebraically that we had been working with in the beginning here, right? So we graphed both of these lines. We said, oh, it looks like it could be around that point, and then we just verified. We found precisely that it is the point 3, 2. It's really important to be able to solve these algebraically, because it's not uncommon that you might solve a system and the solution is like 3.17 and 1.98, and that's hard to guess that, right, when you're doing a sketch. So if we're looking for precision, we want to make sure that we're solving algebraically. The other technique that we have the other algebraic technique that we have for solving a system of equations is to use the method of elimination by addition. Elimination by addition can actually be pretty convenient, especially when solving by substitution could lead to something a little bit, more labor intensive algebraically. And here's the idea. You have to make sure that your equations are written in standard form first. So that means that your x's are aligned on top of each other. Like, look at this equation, the system in 4.9. I have my x's, right? And then, I'm either adding or subtracting, and then I've got my y's next, and then I have equals, and then my constants are by themselves on the other side. That's in standard form, so I want to make sure that I'm in standard form before I do anything else in this system. Now, the next thing we want to do is we're going to pick a variable to eliminate, right? We're always eliminating a variable when we solve algebraically, right? In substitution, we eliminated that variable by making a substitution. That's how we got an equation only with x, right? We eliminated y. Here we're going to pick a variable to eliminate, and in order to eliminate them, we're going to multiply one or maybe both equations by some constant. Each equation by its own constant. And the idea there is that we're going to try to get it so that the two equations, for that variable we've chosen, the result is that their coefficients are equal and opposite each other. And so I'm going to show you what I mean by that here. All right. So let's say we decide to eliminate, x. We could also choose to eliminate y. But I'm just picking x for this example. If I want to eliminate x, I'd notice, right, the coefficients on x are 5 and 2 respectively. I want them to be the same value but one positive and one negative. So I notice, well, between 5 and 2, the least common multiple is 10. So I'm going to multiply the top equation by 2. If I multiply that top equation by 2 all the way through, that means the x term, the y term, and the constant, multiplying through by 2, I get 10x minus 4y equals 24. Now, if I multiply that by 2, and I got a coefficient of positive 10, I got a 10x term, on the next equation, I want that to be a negative 10x. So I'm going to multiply this equation by negative 5. And if I multiply through all terms by negative 5, I get negative 10x minus 15y equals negative 5. Now that I've got those coefficients the way I want them, I'm going to add the two equations together. We're now at step 3 up here. Add these two equations together. Notice that the 10x minus 10x, that zeroes out, right? 10x plus negative 10x is 0. Negative 4y minus, plus a negative 15y, that'll give me a negative 19y. And 24 minus 5 is positive 19. I've eliminated a variable. This is an equation with one variable that's actually really easy to solve, right? It's a one step. I just got to divide both sides by negative 19. So here we are at step 4, solve the resulting equation, and we get y equals negative 1. Now that we know the value of y, we're going to find the value of x, and so that means we're now at step 5. Substitute this value we found into one of the original equations. Either of them will work just fine. So let's say I pick the second equation, right? So my second equation is 2x plus 3y equals 1. I'm going to plug in y equals negative 1. And I get an equation with just x, and then I'm going to solve it. Add 3. So 2x equals 4. Now it's all over but the shouting. divide by 2, and we get x equals 2. So we have both values. Now we're just going to state our answer as the pair x equals 2, y equals -1, or if you like writing it as a point, 2, -1. Got to make sure we put the x first. Okay, so let's solve another couple of systems. Let's try this one in 410. I mentioned before that our algebraic techniques can help us determine the unique solution if one exists, but it can also help us detect when there might be no solution or infinitely many solutions. So let's see what happens here. On this system, I'm going to suggest solving, you could do it either way, elimination by addition or substitution. I'm going to go ahead and pick elimination by addition. I'll notice that the top equation, if I look at the x's, I've got a 2 and a 1. So if I leave the top equation alone, no change, and multiply the bottom equation by -2, let's see, that gives me -2x minus 6y equals -4. Then those x's are equal but opposite in sign, right? I've got a 2x and a -2x. Let's add these together. So the 2x and the -2x, right, those zero out. But look, so do the y's, right? I got a 6y and a -6y. So this left side is 0. On the other side, -3 plus -4 is -7. So look what we have. This equation 0 equals -7. Look, I'm going to say something earth-shattering right now, probably, so brace yourself, but 0 is pretty clearly not equal to -7, right? So we made legitimate algebraic moves, and we got this equation 0 equals -7. This is false. In fact, this is never true. There is not a value of x and y that you could find to plug in that's going to magically make 0 equal to -7. And so what that means is that there is no solution. If you graphed these two lines, they would be parallel lines. So they would never intersect. Let's look at another one here. Let's solve this system of equations. Again, I'm going to choose to use elimination by addition. Looking at the x's, I have a -3x and a +1x. So I'm going to multiply the top equation by 3, but I'm going to leave the second equation alone. So 3x minus y equals -6, and then -3x plus y equals 6. Now let's add these together. You'll see the same thing is happening on the left side. 3x minus 3x, those zero out. -y plus y, those zero out. We get a 0 on the left side. On the other side, though, notice now I've got -6 plus 6. That's 0. 0 is equal to 0, right? This equation is always true. And that means that there are infinitely many solutions. In fact, if we graphed these two lines, they would be the same line, one just on top of the other. Notice in both of these cases, in a situation where there's not a unique solution, right? There's either no solution or infinitely many solutions. Algebraically, we can tell that happens because as we're solving it, we lose our variables entirely, right? They both cancel out. That would happen whether we use elimination by addition like we did in these two, or whether you solved using substitution, you'll see the same thing happen. All right, let's make let's finish up by doing a word problem. So, in this example, we have a coffee shop that sells a coffee blend made from two different coffees, one that costs $5 a pound, the other costs $6 a pound. They sell this blended coffee at $5.60 per pound, and we want to know how much of each coffee is used to obtain 100 pounds of the desired blend. So, how much of each coffee, like how many pounds of each coffee? So there's two things we're trying to find, right? How many pounds of the first blend and how many pounds of the second blend. So I'm going to let that be my variables here. I'll say let's let X be the pounds of the, $5 per pound coffee. And Y can be pounds of the $6 per pound coffee. Now, in these problems, like if we're solving, this is appearing in the section where we're solving systems of equations, we have two variables. They should have given us enough information to write two equations. So one equation in this example is pretty simple to get because we're going to get 100 pounds of the blend, right? That means that when I take however many pounds of that $5 coffee and however many pounds of that $6 coffee and I put them together, I've got 100 pounds all together. So that first equation is just X plus Y equals 100. That equation is just about the amount of coffee, how many pounds. The second equation is going to be about cost, right? So the blended coffee sells for $5.60 per pound. We have one coffee at $5 per pound and the other is at $6 per pound. That's what we're going to kind of use that information to make our second equation. And this is just going to be about cost. So if they take X pounds of coffee and that coffee is $5 per pound, that means that the amount spent on that coffee is 5 times X, right? Dollars per pound times pounds will give you dollars, plus the amount spent on the $6 coffee is $6 per pound times Y pounds. And what we're ending up with is a coffee that is $5.60 per pound times, we know how much we have, 100 pounds. So if you check your units across in the second equation, it ends up being dollars plus dollars equals dollars. That's a good check when you're doing these applied problems, is that within each equation the units are consistent. In the top equation it's just pounds plus pounds equals pounds. So now we've modeled it with a system of equations, and we need to solve. So I'm going to number these equations, and I'm going to I think use elimination by addition again, just because it'll be pretty easy to eliminate one of the variables that way. Let's say if we eliminate X, I'm going to leave equation 2 unchanged. So that'll be 5X plus 6Y equals 560 times 100 is 560. And for the first equation, I'm going to multiply by negative 5. Negative 5x minus 5y equals negative 500. Now we can add these two equations together. The 5x and a minus 5x, those cancel out. Moving on to the y's, negative 5y plus 6y is y, and negative 500 plus 560 is 60. So that means that we know that y is equal to 60, and if we use one of these equations, and I think it's easiest to use the first equation, x plus y equals 100, we know that y is equal to 60, and if we subtract 60 from both sides, we get x equals 40. So now let's answer the question, because the answer to the question, how many pounds of each coffee is used to get this special pound, is not just x equals 40, y equals 60. There's context to this problem. There should be context to our answers. So let's answer this question. That means that we have, let's see, if x is 40, that is 40 pounds of the $5 per pound coffee, and then 60 pounds of the $6 per pound coffee.